The National Electrical Code, or NEC, does not specify a minimum height for electrical metallic tubing, or EMT, used in an overhead outdoor run when the conductors are contained within the raceway. NEC Article 225.18 applies to open conductors and cables, not conductors, within raceways. It requires a minimum height of 10 feet for open conductors and cables below 600 volts. Given that the conductors are contained within EMT and the gap between the structures is not a thoroughfare or near doors, gates, or windows, it would be compliant to run the EMT overhead with a height of 5 feet. When installing EMT, use proper supports and secure the EMT at appropriate intervals. Ensure that the EMT is protected from physical damage. Consider the effects of wind, ice, and other environmental factors on the EMT. Always consult with a qualified electrician for guidance and to ensure compliance with the NEC and all applicable building codes. When it comes to electrical installations, understanding the National Electrical Code, or NEC, is essential for ensuring safety and compliance. One common question that arises is regarding the minimum height requirements for electrical metallic tubing, or EMT, used in overhead outdoor runs. Let's delve into the specifics of this topic, focusing on the regulations and best practices outlined in the NEC. The NEC provides comprehensive guidelines for electrical installations, covering various aspects such as wiring methods, overcurrent protection, grounding, and equipment installation. When dealing with EMT in overhead outdoor runs, it's crucial to understand the distinction between open conductors and conductors within raceways. Open conductors refer to wires or cables that are not enclosed within a protective raceway, such as conduit or tubing. These conductors are typically used for overhead service drops or feeders. On the other hand, conductors within raceways are enclosed within a protective conduit or tubing system, such as EMT, rigid metal conduit, or PVC conduit. The NEC treats these two scenarios differently in terms of minimum height requirements. According to the NEC, Article 225.18, which addresses clearances for overhead conductors and cables, a minimum height of 10 feet is required for open conductors and cables below 600 volts. This requirement applies to overhead service drops, feeders, and branch circuits that are not enclosed in a raceway. However, the NEC does not specify a minimum height for EMT used in overhead outdoor runs when the conductors are contained within the raceway. This means that if the conductors are enclosed within EMT, there is no specific height requirement mandated by the NEC. This distinction is important because EMT provides a physical barrier that protects the conductors from damage and environmental factors. When conductors are enclosed within EMT, they are less susceptible to physical damage from impacts, abrasion, or weather exposure. As a result, the NEC does not impose a minimum height requirement as it does for open conductors. In situations where EMT is used in an overhead outdoor run, several factors should be considered to ensure safety and compliance. Firstly, it's essential to use proper supports and secure the EMT at appropriate intervals. The EMT should be supported by clamps, straps, or hangers that are designed for outdoor use and are compatible with the EMT material. The support should be spaced according to the manufacturer's recommendations and should be securely fastened to the supporting structure. Secondly, the EMT should be protected from physical damage. While EMT provides a degree of protection to the conductors, it's still vulnerable to damage from impacts, corrosion, or other environmental factors. To mitigate this risk, the EMT should be installed in a location where it is not likely to be subjected to physical damage. If the EMT is exposed to potential damage, it should be protected by additional measures such as guards, barriers, or enclosures. Thirdly, the effects of wind, ice, and other environmental factors on the EMT should be considered. In areas with high winds or heavy ice loads, the EMT may be subjected to significant stress. To prevent damage or failure, the EMT should be installed in accordance with the manufacturer's recommendations and should be adequately supported to withstand the expected loads. Finally, it's always recommended to consult with a qualified electrician for guidance and to ensure compliance with the NEC and all applicable building codes. A qualified electrician can assess the specific requirements of the installation and provide recommendations for the proper selection, installation, and support of the EMT. They can also ensure that the installation meets all applicable codes and regulations. In summary, the NEC does not specify a minimum height for EMT used in overhead outdoor runs when the conductors are contained within the raceway. However, it's essential to use proper supports to protect the EMT from physical damage, consider the effects of environmental factors, and consult with a qualified electrician to ensure safety and compliance. By following these guidelines, you can ensure that your EMT installation is safe, reliable, and compliant with all applicable codes and regulations. Understanding the ampacity of conductors is a critical aspect of electrical installations as it directly relates to the safe and efficient operation of electrical systems. Ampacity refers to the current carrying capacity of a conductor, which is the maximum amount of current that a conductor can carry continuously under specified conditions without exceeding its temperature rating. The NEC provides detailed guidelines and tables for determining the ampacity of conductors based on factors such as conductor size, insulation type, ambient temperature, and the number of conductors in a raceway or cable. One of the fundamental principles of electrical safety is to ensure that conductors are not overloaded, which can lead to overheating, insulation damage, and potentially fire hazards. Therefore, it's essential to select conductors with an ampacity rating that is sufficient to handle the expected load current. The NEC specifies various ampacity tables that provide the allowable ampacities for different types of conductors under different conditions. These tables take into account factors such as conductor material, insulation type, and ambient temperature. For example, copper conductors typically have higher ampacity ratings than aluminum conductors of the same size due to their superior conductivity. Similarly, conductors with higher temperature ratings can carry more current than conductors with lower temperature ratings. The NEC also provides adjustment factors for ampacity based on the number of conductors in a raceway or cable. When multiple current-carrying conductors are installed in close proximity, the heat generated by each conductor can raise the overall temperature of the raceway or cable, which can reduce the ampacity of the conductors. To account for this effect, the NEC requires that the ampacity of the conductors be reduced by an adjustment factor based on the number of conductors. For example, if there are more than 3 current-carrying conductors in a raceway or cable, the ampacity of the conductors must be reduced according to the adjustment factors specified in the NEC. These adjustment factors are designed to ensure that the conductors do not exceed their temperature rating even when multiple conductors are installed in close proximity. In addition to ampacity adjustment factors, the NEC also provides correction factors for ampacity based on ambient temperature. Ambient temperature refers to the temperature of the air or surrounding environment in which the conductors are installed. When the ambient temperature is higher than the reference temperature specified in the ampacity tables, the ampacity of the conductors must be reduced by a correction factor. This is because higher ambient temperatures can reduce the ability of the conductors to dissipate heat, which can lead to overheating. To determine the appropriate ampacity correction factor, the NEC provides tables that list the correction factors for different conductor insulation types and ambient temperatures. These correction factors are applied to the ampacity values obtained from the ampacity tables to determine the allowable ampacity of the conductors under the specific ambient temperature conditions. When selecting conductors for an electrical installation, it's essential to consider the expected load current, the ambient temperature, and the number of conductors in a raceway or cable. The ampacity of the conductors must be sufficient to handle the expected load current, taking into account any ampacity adjustment or correction factors. It's also important to select conductors with an insulation type that is suitable for the operating temperature and environmental conditions. The NEC provides detailed guidelines and tables for determining the appropriate ampacity of conductors based on these factors. In addition to the NEC, other standards and regulations may also apply to the ampacity of conductors in certain applications. For example, some local jurisdictions may have additional requirements or restrictions on the use of certain types of conductors or ampacity ratings. It's important to consult with a qualified electrician and to review all applicable codes and regulations to ensure that the conductors are selected and installed in accordance with all requirements. In summary, the ampacity of conductors is a critical aspect of electrical installations that must be carefully considered to ensure safety and compliance. The NEC provides detailed guidelines and tables for determining the ampacity of conductors based on factors such as conductor size, insulation type, ambient temperature, and the number of conductors in a raceway or cable. By following these guidelines and consulting with a qualified electrician, you can ensure that the conductors are selected and installed in accordance with all applicable codes and regulations, and that the electrical system operates safely and efficiently. When working with electrical systems, it is important to understand the concept of voltage drop. Voltage drop refers to the decrease in voltage that occurs along a conductor as current flows through it. This voltage drop is caused by the resistance of the conductor, which opposes the flow of current. As current flows through the conductor, some of the electrical energy is converted into heat due to the resistance, resulting in a decrease in voltage at the end of the conductor. Voltage drop is an important consideration in electrical installations because it can affect the performance of electrical equipment. If the voltage drop is too high, it can cause equipment to operate inefficiently, overheat, or even fail. For example, motors may run slower, lights may dim, and electronic devices may malfunction. Therefore, it is important to design electrical systems to minimize voltage drop and ensure that equipment receives the proper voltage. The NEC provides guidelines for calculating voltage drop in electrical circuits. The amount of voltage drop in a circuit depends on several factors, including the length of the conductor, the size of the conductor, the amount of current flowing through the conductor, and the type of conductor material. Longer conductors, smaller conductors, and higher current levels all contribute to increased voltage drop. The NEC recommends that voltage drop in branch circuits should not exceed 3%, and voltage drop in feeders should not exceed 5%. These limits are designed to ensure that equipment receives adequate voltage and operates efficiently. To calculate voltage drop, you can use the following formula: voltage drop equals current times resistance. The resistance of the conductor can be determined using tables provided in the NEC, which list the resistance per foot for different sizes and types of conductors. Once you have calculated the voltage drop, you can compare it to the recommended limits to determine if it is acceptable. If the voltage drop is too high, there are several steps you can take to reduce it. One option is to increase the size of the conductor. Larger conductors have lower resistance, which reduces voltage drop. Another option is to shorten the length of the conductor. Shorter conductors have less resistance, which also reduces voltage drop. You can also reduce the amount of current flowing through the conductor by using more efficient equipment or by distributing the load more evenly. In addition to calculating voltage drop, it is also important to consider the voltage rating of electrical equipment. Electrical equipment is designed to operate within a certain voltage range, and operating equipment outside of this range can damage the equipment. The NEC requires that electrical equipment be marked with its voltage rating, and it is important to ensure that the equipment is connected to a circuit with the proper voltage. In some cases, it may be necessary to use a voltage regulator or transformer to adjust the voltage to the proper level for the equipment. It is also important to consider the effects of voltage drop on motor starting. When a motor starts, it draws a larger amount of current, which can cause a significant voltage drop in the circuit. This voltage drop can make it difficult for the motor to start and can damage the motor if it is not properly protected. The NEC provides guidelines for sizing conductors and overcurrent protection devices for motor circuits to ensure that the motor starts properly and is protected from damage. In summary, voltage drop is an important consideration in electrical installations that can affect the performance of electrical equipment. The NEC provides guidelines for calculating voltage drop and recommends limits for voltage drop in branch circuits and feeders. To minimize voltage drop, you can increase the size of the conductor, shorten the length of the conductor, or reduce the amount of current flowing through the conductor. It is also important to consider the voltage rating of electrical equipment and the effects of voltage drop on motor starting. By following these guidelines, you can ensure that electrical systems are designed to minimize voltage drop and operate efficiently. Grounding and bonding are essential safety measures in electrical systems, designed to protect people and equipment from electrical shock and damage. Grounding refers to the intentional connection of a neutral conductor or equipment enclosure to the earth, providing a low impedance path for fault current to flow back to the source. Bonding, on the other hand, refers to the connection of metallic parts of an electrical system to create an electrically conductive path. Together, grounding and bonding help to ensure that electrical faults are quickly cleared, reducing the risk of electric shock and fire. The NEC provides detailed requirements for grounding and bonding in electrical systems. The NEC defines grounding as a permanent and continuous conductive path to the earth, which allows fault current to flow back to the source and trip the overcurrent protection device, such as a circuit breaker or fuse. The grounding system consists of a grounding electrode, which is typically a metal rod, pipe, or plate buried in the earth, and a grounding electrode conductor, which connects the grounding electrode to the electrical system. The grounding electrode provides a low impedance path for fault current to flow back to the source, which helps to quickly clear the fault and prevent electric shock. Bonding is the connection of metallic parts of an electrical system to create an electrically conductive path. This includes bonding together metal conduits, metal enclosures, metal equipment, and other metal parts. Bonding helps to ensure that all metal parts of the electrical system are at the same electrical potential, which reduces the risk of electric shock if a fault occurs. The NEC requires that all metal parts of an electrical system be bonded together, including metal conduits, metal enclosures, metal equipment, and other metal parts. The bonding connections must be made using approved methods and materials, such as bonding jumpers, bonding bushings, and grounding screws. The purpose of bonding is to create a low impedance path for fault current to flow back to the source, which helps to quickly clear the fault and prevent electric shock. One of the key benefits of grounding and bonding is that they help to reduce the risk of electric shock. When a fault occurs in an electrical system, such as a short circuit or ground fault, the fault current can flow through unintended paths, such as the metal enclosures of equipment or the human body. If the electrical system is not properly grounded and bonded, the fault current can create a dangerous voltage on the metal enclosures or other conductive surfaces, which can result in electric shock if someone comes into contact with them. However, if the electrical system is properly grounded and bonded, the fault current will flow back to the source through the low impedance grounding and bonding path, which will quickly trip the overcurrent protection device and energize the circuit. This helps to prevent electric shock and protect people from injury. In addition to reducing the risk of electric shock, grounding and bonding also help to protect equipment from damage. When a fault occurs in an electrical system, the fault current can generate heat, which can damage equipment and cause fires. However, if the electrical system is properly grounded and bonded, the fault current will be quickly cleared, which will reduce the amount of heat generated and prevent equipment damage. The NEC provides detailed requirements for grounding and bonding of various types of electrical equipment, including motors, transformers, generators, and appliances. These requirements specify the size and type of grounding and bonding conductors, the methods of making grounding and bonding connections, and the location of grounding and bonding points. It is important to follow these requirements carefully to ensure that electrical equipment is properly grounded and bonded and protected from damage. In addition to the NEC requirements, other standards and regulations may also apply to grounding and bonding in certain applications. For example, some local jurisdictions may have additional requirements or restrictions on the use of certain types of grounding and bonding methods or materials. It is important to consult with a qualified electrician and to review all applicable codes and regulations to ensure that the grounding and bonding system is designed and installed in accordance with all requirements. In summary, grounding and bonding are essential safety measures in electrical systems, designed to protect people and equipment from electrical shock and damage. Grounding provides a low impedance path for fault current to flow back to the source, while bonding connects metallic parts of an electrical system to create an electrically conductive path. Together, grounding and bonding help to ensure that electrical faults are quickly cleared, reducing the risk of electric shock and fire. The NEC provides detailed requirements for grounding and bonding in electrical systems, and it is important to follow these requirements carefully to ensure that the electrical system is safe and compliant. Overcurrent protection is a critical aspect of electrical safety, designed to protect electrical circuits and equipment from damage caused by excessive current flow. Overcurrent can occur due to various factors, such as short circuits, ground faults, or overloads. Short circuits occur when there is an unintended connection between two conductors with different voltage potentials, resulting in a large and rapid increase in current flow. Ground faults occur when there is an unintended connection between a conductor and ground, also resulting in a high current flow. Overloads occur when the current flow exceeds the rated capacity of the circuit or equipment, typically due to excessive load or malfunctioning equipment. The NEC requires that all electrical circuits and equipment be protected by overcurrent protection devices, such as circuit breakers or fuses. These devices are designed to automatically interrupt the flow of current when an overcurrent condition occurs, preventing damage to the circuit or equipment and reducing the risk of fire or electric shock. Circuit breakers are electromechanical devices that use a bimetallic strip or magnetic coil to detect overcurrent conditions. When an overcurrent occurs, the bimetallic strip heats up and bends, or the magnetic coil is energized, causing the circuit breaker to trip and interrupt the flow of current. Circuit breakers can be reset after they trip, allowing the circuit to be restored to normal operation. Fuses are one-time use devices that contain a fusible link that melts and breaks the circuit when an overcurrent occurs. Fuses must be replaced after they blow, as they cannot be reset. The NEC specifies the types and sizes of overcurrent protection devices that are required for different types of electrical circuits and equipment. The size of the overcurrent protection device must be coordinated with the ampacity of the circuit conductors and the rating of the equipment being protected. The overcurrent protection device must be sized to protect the conductors from overheating and to prevent damage to the equipment in the event of an overcurrent condition. The NEC also specifies the location and installation requirements for overcurrent protection devices. Overcurrent protection devices must be readily accessible and must be installed in a location where they are protected from physical damage and environmental conditions. The NEC also requires that overcurrent protection devices be properly labeled to indicate their ampacity rating and the type of circuit they are protecting. In addition to protecting electrical circuits and equipment, overcurrent protection devices also play a critical role in preventing electrical fires. Overcurrent conditions can generate heat, which can ignite nearby combustible materials and cause a fire. By quickly interrupting the flow of current when an overcurrent condition occurs, overcurrent protection devices can prevent the buildup of heat and reduce the risk of fire. The NEC provides detailed requirements for overcurrent protection of various types of electrical circuits and equipment, including branch circuits, feeder circuits, motor circuits, and transformer circuits. These requirements specify the types and sizes of overcurrent protection devices that are required, as well as the location and installation requirements. It is important to follow these requirements carefully to ensure that electrical circuits and equipment are properly protected from overcurrent conditions and to reduce the risk of fire. In addition to the NEC requirements, other standards and regulations may also apply to overcurrent protection in certain applications. For example, some local jurisdictions may have additional requirements or restrictions on the use of certain types of overcurrent protection devices or methods. It is important to consult with a qualified electrician and to review all applicable codes and regulations to ensure that the overcurrent protection system is designed and installed in accordance with all requirements. In summary, overcurrent protection is a critical aspect of electrical safety, designed to protect electrical circuits and equipment from damage caused by excessive current flow. The NEC requires that all electrical circuits and equipment be protected by overcurrent protection devices, such as circuit breakers or fuses. These devices are designed to automatically interrupt the flow of current when an overcurrent condition occurs, preventing damage to the circuit or equipment and reducing the risk of fire or electric shock. The NEC provides detailed requirements for overcurrent protection of various types of electrical circuits and equipment, and it is important to follow these requirements carefully to ensure that the electrical system is safe and compliant. Electrical safety is paramount in any electrical installation or repair. It is important to take precautions to protect yourself and others from electrical hazards. Before starting any electrical work, it is essential to turn off the power to the circuit or equipment you will be working on. This can be done by switching off the circuit breaker or removing the fuse that supplies power to the circuit. It is also a good idea to test the circuit with a voltage tester to ensure that the power is off before you begin working. When working on electrical equipment, it is important to use insulated tools and wear appropriate personal protective equipment such as rubber gloves and safety glasses. Insulated tools help to protect you from electric shock if you accidentally come into contact with a live wire. Rubber gloves provide an additional layer of insulation, and safety glasses protect your eyes from sparks or debris. It is also important to be aware of your surroundings and to avoid working in wet or damp conditions. Water is a good conductor of electricity, and working in wet conditions increases the risk of electric shock. If you must work in wet conditions, use ground fault circuit interrupters, or GFCIs, to protect yourself from electric shock. GFCIs are designed to detect small amounts of current leakage and to quickly interrupt the flow of current, preventing electric shock. When working with electrical wires, it is important to use the proper wire connectors and to make sure that all connections are tight and secure. Loose or corroded connections can cause overheating and can increase the risk of electrical fires. It is also important to avoid overloading electrical circuits. Overloading a circuit can cause the wires to overheat and can damage the circuit breaker or fuse. To avoid overloading a circuit, do not plug too many appliances or devices into the same circuit. If you are unsure about the proper wiring methods or safety procedures, it is always best to consult with a qualified electrician. A qualified electrician has the knowledge and experience to safely and properly install and repair electrical systems. It is also important to follow all applicable codes and regulations when working on electrical systems. The NEC provides detailed requirements for electrical installations, and it is important to follow these requirements to ensure that the electrical system is safe and compliant. In addition to following safe work practices, it is also important to maintain electrical equipment properly. Regularly inspect electrical cords and plugs for damage and replace them if necessary. Keep electrical equipment clean and free of dust and debris. Do not allow electrical cords to be pinched or crushed, as this can damage the insulation and increase the risk of electric shock. If you notice any signs of electrical problems, such as flickering lights, sparking outlets, or burning smells, have the problem checked by a qualified electrician as soon as possible. Ignoring electrical problems can lead to more serious problems and can increase the risk of fire or electric shock. In summary, electrical safety is paramount in any electrical installation or repair. It is important to take precautions to protect yourself and others from electrical hazards. Before starting any electrical work, turn off the power to the circuit or equipment you will be working on. Use insulated tools and wear appropriate personal protective equipment. Avoid working in wet or damp conditions. Use the proper wire connectors and make sure that all connections are tight and secure. Avoid overloading electrical circuits. If you are unsure about the proper wiring methods or safety procedures, consult with a qualified electrician. Follow all applicable codes and regulations. Maintain electrical equipment properly. By following these safety tips, you can help to prevent electrical accidents and injuries.